Hello everyone. So this will be our second session for LTE KPI optimization. Today we will cover RRC success rate for LTE, and in that we will first cover the RRC KPI and its call flows, because we need to understand the call flows first to understand where the KPI pegs. And then we will talk about the major limitations that we have and what are the optimization actions we can take to mitigate or resolve the issue. So let's start. Firstly, let's understand what is RRC success rate and why we need RRC setup. So, firstly, a user that is, let's say, in idle mode and it needs to connect to the LTE network, it needs to go through RAJ and RRC phase. Now, why is that? Because you need to have a connection to the network, and for that you need to tell the network that you need some resources, right? So, the first thing the UE does, it will do a random access. This is where the UE sends a preamble to the eNodeB, and in response to that, the eNodeB responds with random access response. This message carries the timing advance. So the UE, once it gets that, it knows what is the timing advance it needs, or the timing offset it needs, to ensure that it is uplink synchronized with the eNodeB. Now, after that, the UE sends the RRC connection request. It's also called as message 3. The message 3 because the first message is preamble. The second message is from the eNodeB, random access response, and the third message is message 3, which is the RRC connection request. And this is where the eNodeB pegs the RRC attempt. So our RRC KPI starts over here. If we have, let's say, a high number of RAJ failures, if the user is sending preamble and we are not getting it, or the user is getting the random access response but we are not getting the RRC connection request, in those cases RRC KPI will not be impacted. So RRC KPI starts at this point at message 3. Any issues before that will be pegged in the RAJ KPI, but they will not really be pegged in the RRC KPI. So over here the RRC has different types. Let's understand each type. There are many types, but the major types that we have are mobile originating data, mobile originating signaling, and mobile terminating access. Now, in simple words, what does it mean? Let's see. If let's say I have a mobile and I want to send something. Let's say I want to send a WhatsApp message. So what I will do is I will try to connect to the network with the course code mobile originating data, because I need to send some data. Now similarly, if I have a mobile phone and I'm moving from one place to another, such that I change the tracking area code, so in that case I need to do a tracking area update. In that case, the RRC connection request will have the course code of mobile originating signaling. So similarly, if I have a mobile and I have an incoming voice call, or let's say someone is sending me a WhatsApp message, then I will get a paging request from the system, from the network. In that case, once I get the paging, my RRC connection request cause type will be mobile terminating access. So looking at the course code, we can find out what was the type of service the UE wanted. What was the type of service the UE wanted to access the network. So this is something that we can get from this kind of messaging. Now what happens after that? The eNodeB reads the RRC connection request, and then it responds with RRC connection setup. This one carries some of the immediate network configuration which is required by the UE to start the network connection or RRC connection setup completion. So after reading this configuration, the UE applies this configuration and responds with RRC connection setup complete message, and this will be message number 5 as well. So when the eNodeB gets this message, at this point the eNodeB says okay, the RRC is successful, and we say our KPI for success is pegged. So RRC success over RRC attempt is what we call the RRC success rate KPI. Now some of the important timers here, for instance we have UE timer, which is T300, which the UE starts once the UE sends message 3, and it stops when it gets the message 4, which is the RRC connection setup. Now if this timer is too small, then the UE will stop this timer and send RRC connection request again. So we will have a failure at the eNodeB end, because eNodeB will have sent this message much later, before the timer already expired, and this message will never come. So this timer, if we increase this timer, we have a higher probability of receiving the RRC connection setup, especially when we have congestion on the eNodeB. Then this timer can come into play. Another one is over here on the eNodeB side. Once the eNodeB has sent the message 4, which is RRC connection setup, then the eNodeB waits for message 5, RRC connection setup complete, and this one is governed by a timer at the eNodeB side. Now this timer, if it is small, then if it expires, the eNodeB will consider it an RRC failure, and thus we will have a lower RRC success rate. So this timer, increasing this timer can also increase the probability of RRC success rate KPI. So these are the two basic timers that we have on the RRC part. Now let's move on and understand the most important kind of failures or limitations we have on the RRC success rate. So one of the most common issues that we face for LTE RRC success rate KPI is the RRC failure due to no response. Now what does that mean? That means that the UE sent RRC connection request, eNodeB responds with RRC connection setup, but after that the UE sends RRC connection setup complete, but the eNodeB does not get it, or eNodeB could not decode it. So in that case we see an RRC success failure, and we have a lower RRC success rate. This is the most common scenario, which is normally seen in coverage scenarios. So when you have a coverage issue, the RRC connection setup complete will have a higher problem. Now, why would this happen? Let's understand this. The most common issue why this happens is basically the MO signaling problem. Now, if we understand this, the RRC connection request is also an uplink, while RRC connection setup complete is also an uplink message. So why does it happen that this message is successfully decoded, but sometimes this message is not successfully decoded for the same UE? So it happens because of the size of this message. So let's understand this. Now consider this scenario first. We have a user using RRC connection request for MO data or empty access. Now this user, what it will do is that it will send the RRC connection setup complete, which will be a much smaller packet. It will be maybe around 10 bytes only. So if it is 10 bytes and it only needs 2 resource blocks, so the power of the UE is distributed only among 2 resource blocks. While the mobile originating signaling message, it carries the NAS messages, which is the attach request or a tracking area update request. So it is a much bigger message. It can go up to 100 bytes, 150 bytes. So when it's a big message, it needs more resource blocks. So let's say in this example, we have 10 resource blocks. So the power of the UE needs to be distributed over 10 resource blocks. So that means the power per resource block will be much lesser. So let's take this example. So in this case, let's say in MO data, let's say the UE's power is 200 milliwatts, and we know that it used 2 resource blocks. So the power per resource block will be 200 milliwatts divided by 2 resource blocks is equal to 100 milliwatts. So for MO data, the RRC connection setup complete is carrying the resource blocks with the power of 100 milliwatts per resource block. The same UE, when it sends an MO signaling RRC connection setup complete, in that case it takes, let's say, 10 resource blocks. So now the power per resource block is 200 divided by 10 is equal to 20 milliwatts. So we can see that the power per resource block is now 5 times lesser compared to MO data or empty access. So what will happen at the eNodeB side, it's easier to decode a message which has higher power compared to a message which has lower power. So the chances of failure for RRC setup complete for MO signaling is that's why much higher. So if you compare the RRC setup success rate for MO data, empty access and MO signaling, you will most probably see that MO signaling has a much lower RRC success rate. So that also means that in a network where you have more MO signaling based RRC connection requests, that network will have a lower RRC setup success rate KPI. And why the networks will have more MO signaling? Let's say if one network has a smaller tracking area codes, a smaller TAC. So what will happen is that it will have more tracking area updates. Another network which has bigger TACs, so it will have lesser tracking area updates, so it will have lesser MO signaling. So this kind of scenario, you can check for your network and find out how much of the RRC connection requests are coming from MO signaling, and if it is too high, then your RRC connection setup success rate would be a bit lower compared to other networks which have lesser count of MO signaling. Another problem of MO signaling can happen is because of ping pong between 3G and 4G, for instance. Every time UE goes to 3G and comes back to 4G, it needs to do MO signaling, either tracking area update or attach. So that can also cause more MO signaling request for your network. Okay. Another normal issue that can cause this RRC connection setup complete issue is interference. If eNodeB is facing interference issues, then it is possible that it is unable to decode uplink messages. That can also impact the RRC success rate KPI. Now, if you have interference, then maybe you can activate interference rejection combining the IRC algorithm on the eNodeB. That usually helps. Or moreover, the interference has different types. If you see interference that it is higher during daytime and lower during night time, so it means that it is somehow related to the network load. So that is okay. In that case, normally down tilt might help in improving your interference scenario and also your RRC and other KPIs as well. If you see that the interference is high both in during daytime and during the night time, then that is usually the scenario where you have a signature of external interference. So in that case, you can check if the interference is on the full band or it is on the partial band. If it is, let's say, only part of the band is interfered, then you can schedule your uplink data in the area which is uninterfered. That can also improve your KPIs. So these things can happen and help you in interference scenarios. Another problem that usually happens or can happen is incompatible UEs. So let's say a UE that has sent an RRC connection request, eNodeB responds with RRC connection setup, and UE finds out inside the RRC connection setup that it does not support this configuration, then it might stop over here and do not send the RRC connection setup complete. In that case, it might try again for RRC connection request, and it will again get the RRC connection setup which it says it is not compatible with. It will again fail. So such incompatible UEs can keep on attempting to access the network, and in short, they can really screw up the KPI. So for such issues, what you can see is that you can put a trace on the RRC layer, and inside the RRC connection request, you can look at the TIMZ. If the TIMZ of a UE is same for multiple requests, you can find out that this is the UE which is the problem, and you can find out that it's not a network issue but a UE issue. So these are some of the tricks we can do for RRC failures, especially for the no response issue. Now another option would be an RRC failure due to rejection. Now this happens in the scenario when a UE sends RRC connection request and eNodeB responds with RRC connection reject. Now here the UE will again have an RRC setup failure, but this kind of failure usually happens when the eNodeB is congested. Either it can be that it has reached its connected user limit, or it has some kind of admission control algorithm running, or it has reached its limit of license, or it has reached its signaling limit, number of calls per attempt, for instance. So the number of call attempts per second, for instance. So this kind of issues can cause RRC rejections, and they usually happen in case of, let's say, high traffic events or sites which are very highly congested. So in that case, the UE gets the RRC connection rejection, then it waits for timer T302, and once T302 expires, then it can try sending RRC connection request again. So this timer is sort of a hysteresis to ensure that one user or multiple users do not storm the eNodeB with multiple requests after a rejection. So this is one of the timers that we can use to somehow play in certain scenarios when we have high rejection rate. So if we increase this timer, then what will happen is the UEs will send RRC connection request more further apart, and in that case we have a chance that we will not have congestion. Now another scenario would be, let's say let's take this example. Now we have an eNodeB which is at full capacity because let's say it has a capacity of 5 users. So it says all 5 users are connected, so eNodeB does not have any more capacity. So if a UE from idle mode tries to connect now, it sends an RRC connection request. The eNodeB will send an RRC connection rejection. So this UE will then be rejected and we will have a RRC failure or the eNodeB side. Now what will happen? Now what can we do for this scenario? One of the quickest way to resolve this kind of problem or to relieve this congestion is the inactivity timer. So if we reduce the inactivity timer, IAT, I mean inactivity timer, if we reduce that, what will happen is that the UEs that are connected will be released quickly due to inactivity. So if the inactivity timer was, let's say, 20 seconds and I make it, let's say, 2 seconds, then all the users will start getting released quickly because the moment they go into idle mode, they were previously waiting for 20 seconds and then getting released. Now they will only wait for 2 seconds and the eNodeB will release them, so the UE will move to idle mode quickly. In that case, we will have more capacity over here. Now the drawback on this one would be that when you release more UEs to idle mode, then they attempt again to connect, so you will have more RRC connection requests. So if the eNodeB is having a problem of let's say connected user limit, but it has no problem of call attempts per second, or we also call it caps, then this will help. If the eNodeB is having no issue of connected user limit, but it is having a problem of call attempts per second, then actually we can increase the inactivity timer. In that case, more users will be retained in connected mode and they will not be released to idle mode, and we will have less number of RRC connection requests. So the inactivity timer can actually, we can play with it to ensure that we get the optimum results. Also another point would be that if we have lots of users on one band, or let's say on one eNodeB, then we can actually use mobility strategy or load balancing as well to shift users from this site to another site, or from this band to another band. So if it is a mobility based load balancing, will actually keep looking at the congestion on this one and also on the target nodes, and if you lower the threshold for mobility load balancing or make it more aggressive, it will start moving these users to the uncongested band or uncongested sites. So that can also reduce your congestion to a certain extent. So these are some of the things that we can do. Another problem that can happen for causing RRC connection rejection can be the PUCCH capacity. Now PUCCH in uplink, it has a limited capacity because it has to multiplex users for their CQI, HARC acknowledgements and HARC feedback and scheduling requests. So when you have lots of users, it is possible that your PUCCH capacity has reached its limit. In that case as well, the eNodeB can send an RRC connection reject due to PUCCH congestion. So in those cases, if you see those cases, you can actually expand the PUCCH by using the features like dynamic or adaptive PUCCH. In that case, the eNodeB keeps on checking the demand, and it can give more resource blocks to PUCCH such that it can expand its capacity, and it will not result in a rejection at RRC level for PUCCH based congestion. So these are some of the tricks that we can do for RRC rejection scenarios. So that's all for today. I think we have two major scenarios. One is the RRC setup failure due to no response, so we covered that as well. Second is the RRC failure due to rejection. We covered this one as well. The most common one is still the RRC failure due to no response, because that's something that happens everywhere. It's more of a coverage related issue, and we can see the different things that we can do for that. For RRC rejections, that's more like an issue where we have congestion or high traffic events, so it's not something that you will see every day, but still it's good to know what causes that and how to tackle that as well. So thank you so much for today. The next session on LTE KPI optimization will be LTE drop rate, so stay tuned for that. Do subscribe, and see you soon. Bye bye.